Hello, students. We're jumping into the math connections on 4.1. And I do want to bring up a couple pieces here, especially in that first one, which I think is just a really good question for us as we move forward. When you're having to justify something, it's so tempting to say, let me just find a bunch of examples. And that's not an appropriate response because just a bunch of examples shows that it works for those examples. It does not show that it works in general. So let me give you an example here. With some of these pieces. So it says, notice, assume n is a natural number. This is question 1. I'm pretty sure this is, I think I did 1, 3, 5, 7. So assume n is a natural number. So notice it says if n squared is odd, then is it true that n has to be odd? So you have to take a number and square it, and you have to get an odd number out. And so what happens is sometimes people do like 3 or 4 examples, and then that is good enough for them. You're about to be a teacher, so remember, if you do something with 3 or 4 times, it might work 3 or 4 times, but it may not work in all cases. So when we have if-then statements, we need it to be true all the time. So let me show you kind of a technique, and the reason why we went through chapter 2 is to say, look at this question. If n squared is odd, then n is odd. So this is one of the statements like we saw back in chapter 2. We have a statement P, we have a statement Q. This is equivalent to saying if P, then Q. And you may look at this statement and say, I'm not exactly sure how to start that one. How would I start with a squared number that has to be odd? Okay. And then how would I be able to show that the original number has to be odd? Every time I try it, it seems to work, but how would I show that in general? And this one is a little bit more challenging. So what I want to remind you of is your ability to rewrite an if-then statement as something that's equivalent. And something equivalent would be the contrapositive. And so what you can do, and I'm recommending that you do here, that's why I assigned this problem, is to rewrite the problem so that you now have the contrapositive. Let's take a look. So again, this piece comes into the front. I would keep an if statement here. If n is not odd, well, if it's not odd, it must be even because we're dealing with natural numbers. So if n is even, then what? Then, so I'm negating it. That's why I said it is not odd. Then I need n squared to not be odd. So I want to say n squared is even. So what I've done is I've rewritten the problem in a way that now if I come to start this problem, my if portion says n is even. Okay, so you could start with that and say, okay, if n is even, n is even means what? That n is equal to 2 times some number. And that number would have to be a whole number. All right, so now I've got that. Assuming that is true, now I'm trying to prove that n squared is even. That's what I want to show. So I need to actually go and find what does n squared look like. Well, n squared would be n times n, which would be 2m times 2m. You can put parentheses around it if that's helpful. And 2m times 2m turns out to be 4m squared. Now the question to you is that an even number? Now remember, even means it's divisible by 2. So does 2 divide this number? And we could say 2 divides 4 definitely, right? We know that 2 divides 4. So 2 divides 4 times m squared, and go back to your theorems and say that was theorem 4-1. If it divides a number, it divides any multiple of a number. And then you can conclude by saying thus, n squared is even because you just show that 2 divides it perfectly. So let me jump here and kind of highlight then. At least I think so. Where is it? Vanishing pen? No, highlighter. There we go. Okay, let me jump to highlighter real quick so you can kind of see the piece I'm talking about. So what did we do? We started here with n is even. So this whole problem is if n is even, and then we kind of worked our way down to where we showed n squared is even. So you now have a, if n is even, I guarantee that n squared is even. And that's a really big claim to be able to make. You now just proved the statement has to be true. Now, all of these statements are true. They're asking you to justify them. So take a look at the next one. If n squared is even, then n is even. Again, maybe that would be a tough one to start with. Try writing the contrapositive instead of just writing out, instead of trying to prove that one directly. Here, if n plus m is even, then n and m are both even or both odd. Okay. So you could start with that piece. You could do the contrapositive on this one. Totally up to you. Part D, it says if n and m are odd, then the product, and you multiply them together, that's odd. Okay, well, as it turns out, you could go back to some of the videos I've done, or you can go back and look in a book, but they've done things like this where start with what it means to be odd. If it's odd, then n is equal to 2 times a plus 1, and m is odd, so it's equal to 2b plus 1. Then multiply those together and see if your result turns out to be an odd number, which would be 2 times something plus 1. That's what an odd number kind of looks like. Very cool. And again, I'm going through that one in a little bit more detail because I think when you're coming into this class, it might be rare that you've had to actually justify something, which means show that it's always true. So I'm trying to give a little bit more time to that. What else do I have here? Jim wants to see if a number is divisible by this. He divides it on his calculator, gets this. Does it divide evenly? Why or why not? So explanation, do you understand that? Then if you divide and the calculator displays 16.8, does it divide? Why or why not? So again, a definition piece, good question to talk about the definitions. Number 5, if a number is not divisible by 5, can it be divisible by 10? If it's not divisible by 10, can it be divisible by 5? Great questions because it's talking about those if-then statements again. Okay. Let's see here, and the number 7, I believe, was assigned 357. What did I do? 1357. Okay. So 7, enter any 3-digit number on a calculator, then repeat that to 3-digit number. So do it twice, enter it twice, and then divide by 7, divide by 11, divide by 13. What is the answer? And then try it again with a different 3-digit number. Will that always work? And so if you're thinking about it, if you are dividing by 7, 11, and 13, picture in your mind, you've divided by all those pieces. How would you go backwards to find out what you multiplied to get to the large number? So I think this is a question about the idea of division and how it kind of can be linked to multiplication. And then I did a couple of the classroom ones. I think I did 12 through 16. Yep, 12 through 16. So Jamila claims 10 is both even and odd because it's divisible by an even number and divisible by an odd number. How would you respond? So again, be thinking to yourself, first off, is her claim correct? Right? Is the claim that it's both even and odd correct? Okay. Then think through, why would someone make that claim? Right? What must be true about this? And then try to tie it back into, if the student is on the wrong track, try to guide them back towards the actual, is this even or odd piece? Let's see here. Sabine claimed the whole number is divisible by 4 if each of the rightmost 2 digits are divisible by 4. Okay. Now this is different. So again, sometimes students read through the wording of the question, I should say. It says if each of the rightmost 2 digits is divisible by 4. Now we already had a case that we've been working with where we know that 4 times 25 is 100. So all multiples of 100 are guaranteed to be divisible by 4. And that's why whatever number we might have chosen, all we did is look at the last 2 digits because everything else is groups of 100. So we know that it works. But that's not what Sabine is claiming. She's not saying the last 2 digits or the rightmost 2 digits. That number is, so she's not looking at the 43. Sabine is looking at a 3 and a 4 separately because it says if each of the rightmost 2 digits is divisible by 4. Okay, so take a look, see if you believe in that claim. Is she on the right track? Is she not? Let's see your 7th grade class, completing unit on divisibility rules. One student asked why divisibility by 6 cannot be tested by dividing the sum of the digits by 6. Okay, so why not, right? And so you can check that, but it may also be thinking of maybe connecting that back to divisibility by 3. Why do we get to divide by 3 by checking the sum of the digits? 15, a student claims a number is divisible by 24 if and only if it's divisible by 6 and 4. Okay. And in general, number is divisible by a times b if and only if it's divisible by a and b. So you want to check that. Now remember, if you want to prove something true, you have to verify that it is always true. If you want to prove that something is false, you just need one counter example. And so that's what I might recommend here. When you see something like this, remember the rule for 6. For 6, we would check 2 and 3. So maybe the student's leaning in that direction, right? They're thinking, oh, then it works for any numbers. But there was something special about 2 and 3. They had no common factors. And so if you go back to those Venn diagrams, if they do share a common factor in the intersection, then this rule may not work well. Okay, so let's take a look at things that are divisible by 6 and by 4. So let's look at multiples of 4. Just as an example, this would be like from chapter 1. Write out what I know. Multiples of 4 would be 4, 8, 12, 16, 20, 24, right? Right. Keep going. 28, dot, 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 dot. Okay. Now, some of these might also be divisible by 6. 4 is not divisible by 6. 8 is not divisible by 6. 12, yes. 16, no. 20, no. 24, yes. 28, no. If we kept going, 32, no. 36, yes. Okay. But now if you look at the result, look at the numbers that are showing up here. 12, 24, 36. So what we're doing is we're forming a sequence of numbers that is always off by 12. So now the student is claiming that every one of the numbers pointed to with these arrows, every one of them is divisible by 24. So you found numbers that are divisible by 6 and 4. Does that mean that it must be true that it's divisible by 24? And vice versa. If it's divisible by 24, does that mean it's divisible by 6 and 4? Those are two completely different questions. Okay. All right, and lastly, number 16, Alejandro claims 0 is neither even nor odd, because to be even, you got to divide it into 2 equal piles, and to be odd, you'd have to divide it into 2 equal piles. You would not be able to divide it into 2 equal piles. So what is your response to convince him that 0 is even? Okay, so we know 0 meets that. Maybe go back and say, well, how are you picturing even and odd? So divide it up into 2 equal piles. Picture kind of, is it divided up into 2 equal piles? And it's not necessarily, I think maybe I might focus in on the, what does it mean to be odd? In order to be odd, 0, the number, would not be able to divide it into 2 equal piles. You may want to clarify. It's a little bit stronger than that. It's not that it just can't be, it's that it would be 2 equal piles and have 1 left over. So that might be a good way to kind of push the student to say, that's why 0 is not an odd number, is because to be an odd number, it has to meet the even definition and be 1 more than that. So again, there's a good way to kind of push a little bit to kind of say, here's why it might not meet one definition, but make sure you go back to the definition. What does it mean to be an even number? What does it mean to be an odd number? Okay. All right. Well, that takes care of 4.1. We'll see you next week with that, and hope everything's going all right. Have a great day. Off you go.